IP addresses, how devices find each other. Every connection on the internet uses one. Every log entry records one. Every attack traces back to one. IP addresses are how devices find each other. And if you are going into cybersecurity, you'll be reading, analyzing, and tracing them every day, almost every day. Let's break it down. An IP address or Internet Protocol address is a number assigned to every device on a network. It's how that device gets identified and located. When your computer requests a web page, it sends that request from its IP address to the server's IP address. The server sends the page back to your IP address. Without these addresses, neither side would know where to send anything. Think of it like a mailing address. The postal service doesn't care about your name, it just needs the address to deliver the package. IP addresses work the same way for data. In 2026, IP addresses aren't just on laptops and phones anymore. Every IoT device, every cloud instance, every container, serverless function, they all have IP addresses. A single company might manage tens of thousands of IPs across physical offices, cloud environments, and remote workers. Understanding how they work is foundational to understanding how any of that infrastructure connects. IPv4 addresses look like this: 192.168.1. 4 numbers separated by dots. Each number ranges from 0 to 255. This gives us roughly 4.3 billion possible addresses. That sounded like plenty in the 1980s when the system was designed, but with over 20 billion devices connected to the internet today, we ran out of IPv4 addresses years ago. Despite that, IPv4 is still everywhere. Most of the internet still runs on it. Most firewall rules, most log entries, most tools, you'll see IPv4 addresses constantly. The format is simple enough that you'll start recognizing common patterns quickly. 10.x.x.x and 192.168.x are private ranges. 8.8.8.8 is Google's DNS. You'll develop an intuition for what normal looks like and what doesn't. IPv6 was created to solve the address shortage. An IPv6 address looks a little different to IPv4. It's longer, uses hexadecimal, and provides practically unlimited number of addresses. It's enough to give every grain of salt on earth its own IP address multiple times over. The transition from IPv4 to IPv6 has been slow but steady. As of 2026, roughly 45% of global internet traffic uses IPv6, up from about 30% a few years ago. Google, Facebook, and most major services support it fully. Cloud providers assign IPv6 by default on new infrastructure. You need to understand both, but you'll encounter IPv4 far more in day-to-day security work. For now, from a security perspective, IPv6 introduces some specific considerations. Its massive address space makes traditional network scanning harder. Some security tools still have gaps in IPv6 support. And dual stack environments, networks that run in both IPv6 and IPv4, can create blind spots if only one protocol is being monitored. So let's look at public versus private IP addresses. Public IP is the address your network uses to communicate with the internet. Assigned by your ISP, visible to every server and website you connect to. When someone says they can see your IP, They mean your public IP. The private IP is your address your device uses inside your local network. Your router assigns these. Your laptop might be 192.168.1.5. Your phone 192.168.1.6. Your smart TV 192.168.1.7. These don't work on the public network. They only work within your local network. Let's look at an analogy. Your public IP is the street address of an apartment building. Your private IP is your apartment number. People outside use the street address. Once inside, the apartment number is what matters. The device that translates between them is your router. Using NAT, which is Network Address Translation, when your laptop sends a request to a website, the router swaps the private IP for the public one before sending it out. When the response comes back, the router remembers which device requested it and routes the data to the correct private IP address. It's like a receptionist forwarding calls to the right extension. This same concept applies in cloud environments. When you set up a VPC in AWS or Azure, you define private IP ranges for your cloud resources. They communicate internally using private IPs, and NAT gateways or load balancers handle the translation to public-facing addresses. Same fundamentals, different infrastructure. The 3 reserved IP ranges you should memorize: Class A, which is 10.0.0.0 to 10.255.255.255. This is used by large enterprises and cloud environments. It's a massive range. Class B. These are for medium-sized networks, starting at 172.16.0.0 to 172.31.255.255. And then we have Class C, your home networks. You'll see this one the most in personal setups. The address space starts at 192.168.0.0 to 192.168.255.255. Let's look at static versus dynamic IPs. Your static IP stays the same every time. Servers use static IPs because other devices need to find them reliably. If a web server's IP address changed every day, DNS records would break. Database servers, domain controllers, network printers, anything that needs to be found at a consistent address gets a static IP. A dynamic IP is assigned automatically by a DHCP server, usually your router. And this can change. Most end-user devices get dynamic IPs. Your laptop probably doesn't have the same private IP it had last month, and that's fine. From a security standpoint, when you see a static IP in logs, you can reliably map it to a specific device or server. Dynamic IPs require checking the DHCP logs to figure out which device had that address at that time. During incident response, matching a dynamic IP to a specific device at a specific timestamp is a common task. Why do IP addresses matter in cybersecurity? Let's look at log analysis. Every firewall log, server log, and SIEM alert contains IP addresses. You're looking at source and destination IPs to figure out who's connecting to what. An unfamiliar external IP hitting your server thousands of times per minute? That's worth investigating. Tools like Splunk, Microsoft Sentinel, and Google Chronicle will organize data around IP addresses. Tracing IPs is one of the first steps. Where is this traffic coming from? Is it an internal IP address, suggesting a compromised device or an insider threat, or an external one? What country does it geolocate to? Is it on any known bad list? AI-powered tools can now correlate IP data across multiple sources in seconds. But you need to understand what the results mean. Network segmentation. Security teams use IP ranges to separate network segments. Your accounting might be on 10.0.1.x, engineering on 10.0.2.x, guest Wi-Fi on 10.0.99.x. If an attacker compromises one segment, proper segmentation prevents lateral movement to the others. Zero trust architectures take this further, even if devices on the same network don't automatically trust each other. Threat intelligence. Security teams maintain block lists of known malicious IPs. If traffic from one shows up on your network, that's an immediate red flag. Threat intelligence feeds from providers like CrowdStrike and Palo Alto, as well as open source sources like Abuse IPDB, are constantly updated. Modern SIEMs can automatically cross-reference incoming traffic against these lists and alert on matches. And lastly, cloud and container security. In cloud environments, IP addresses are ephemeral. Containers spin up and down. Auto-scaling groups add and remove instances, and serverless functions execute and disappear. Security tools need to track IPs dynamically, and logging needs to capture enough context to reconstruct what happened. Understanding IP behavior in cloud-native environments is increasingly important. IP addresses are the addressing system of the internet. Every connection, every attack, log involves them. You don't need to memorize subnetting tables on day one, but you do need to understand public versus private, static versus dynamic, and IPv4 versus IPv6. Once you do, everything else in networking and security builds on top of it. Next up, the actual hardware. Routers, switches, firewalls. What each one does, how are they different, and why does it matter for security? Subscribe so you don't miss it.